Homework 22, page 298, section 5.1. Yes, we're going into chapter 5. And it's only, what, 8 problems? One of them is an even problem. And these are difficult. 20 and 21 are pretty difficult. But hopefully I will give you enough today that it won't be difficult. It could be difficult. So, okay. Extra credit. We're going to redo this problem. It'll be due Tuesday, 1 week from today. Now, let's talk about this real quick. All right, look. First off, here's the setup, right? You have this function, right? And you are to inscribe, it is to be inscribed in a triangle, right? An isosceles triangle, meaning this and this, right? This one and this one are the same. This side and this side are the same. And the base is whatever the base is. Now, I suggested that you forget about this and just work on that side. And then at the very end, if you've optimized that, right? And the problem is to find the triangle of minimum area, right? Minimal area. You're trying to minimize the area of this triangle. Now you could, I mean, it's quite literally, if you do this and multiply it by 2, it's quite literally the same thing. It's just, it's easier to focus on stuff, especially when all of your x's and y's are positive over here. It's a lot easier to think about. But you could do the whole thing. I've just suggested that you forget about this half, use symmetry to say, whatever I do here, I'll multiply it by 2 at the end. Or at some point in there you multiply it by 2. Whatever. Now, here's the thing. The thing is, this has to, the triangle has to inscribe the parabola. And for that to be the case, right, what that means is that it touches at one point, and it should be kind of obvious. The only way that something could touch a curve at one point is if it's tangent right there. Okay? Now, let's just think about a couple things. So, on one hand, really this question boils down to is like, where does it touch? Because we've seen, like I was trying to show in class, if it touches way, 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 way up here, well, your triangle could potentially be infinitely large. You don't want to maximize the area. There is no maximum area because you could make it arbitrarily large. So, and I also said that this point is that it touches is not right here. It's not that point. Like, you could do that. Like, there is a tangent line that touches right there and it inscribes this. And I'm just telling you that ain't what we're looking for. That's not the one that minimizes the area of the triangle. So what you're going to need, right? What you're going to need to have is a function. Because you're trying to minimize the area. You want a function that has some input, and the output is area. That way, you could take the derivative of this function, set it equal to 0, and find out what you're trying to find out. I could just tell you some stuff right now, but I'm not going to. So, because I want this to be somewhat challenging, because this is a challenge. I told you this is a really hard one. This is one of the hardest ones I've ever seen. But not for the reasons that you guys made it hard on yourselves. Like, that's why I want you to redo it, because you'll see how stinking hard this gets when you have the right idea. So, I've said all that, right? So, what this comes down to, really, is where does it touch? And if you could somehow get a function that it's like, where does this touch right here? That's the big question. And if you could get an area function that takes the input, where does it touch, and the output is area, that's exactly what you're looking for. Then you just take the derivative of it, set it equal to 0, and it will tell you where does that touch. A couple other things though, is that you're going to need a constraint. And I don't see how much I wanted to say here. So you want to use these two things, right? Obviously, this side of this is a line. Every line has this form. And a couple things here. Like, one, wherever this touches, don't know where it touches, but wherever it does touch, then the slope of this thing has to be the same as the slope of this line. But obviously the slope of this changes, right? It's not the same everywhere. So it has to be the same at, well, we don't know where. That's the idea. So that's one constraint that you have. Another constraint is that they have to touch, right? Yeah. So wherever, in other words, whatever you plug in here, whatever that is, not sure what it is, but when you plug it in, that has to be the same thing as this. You have to, those lines have to touch. Whatever this output is, call it y, I don't know, star. It's your special value of y. When you plug this into there, you get out that y star. Whatever that number is, we don't know. Ditto here. When you plug in your thing, out has to pop y star. That's what that means. And so you could use these things right here to constrain this right there. And I'm just going to tell you that so here's another hint. Choose your variables wisely. There you go. Okay? Due Tuesday. That's all I'm going to say about that. And again, this is extra credit, so you could just not do it. Really, I mean, I want you to try it. So given that, right? Like that's just stuff that, that's just the way it is with this problem. Even with all those hints, this is going to be a very difficult problem. That's why, and I want you to go knowing that stuff. I want to see what you do with this problem. It might just be that you just say, well, let me just try this, and it just works. And you get, remember I told you this, area is equal to what?
1/2.
No, yes, it's 1/2 the base times the height. But what did you guys watch the, yeah.
2 over r root 3.
8 root 3 over 9. The area that does, the minimal area that you're looking for is this, and that is how you're going to check your, that's how you're going to check your answer. If you don't get this as the area, you're wrong. Keep going until you get this as the minimal area. Okay? Okay, everybody good? Okay, very difficult problem. And again, I want you to, even with all that, you start doing it, you're going to run into some stuff and go, what is going on? Unless you just happen to get it, in which case that would be really cool. But it's tricky for a reason that I want to get into, and I can't get into that until you guys try it that way. Okay, so here we go. Moving into chapter 5. Remember day 1 of calculus. I said, let's say that you get on I-5 at mile marker 100, and that's when you start your clock. 0. Time is 0. And you're driving 60 miles per hour. And you drive for 2 hours. How far have you gone? Well, first off, we could say this is your position as a function of time. It's a line because you're going a constant speed. What's your constant speed?
60 miles.
60 miles per hour. And so your mt plus b, your slope has to be 60 t plus, and we said we know where we start, so it's 100, right? And so you could, if you say, okay, how far have you gone? One way to do that is say, well, after 2 hours, I could just plug that into here. I get my p of 2 is 60 times 2 plus 100. That's 120 plus 100. I end up at mile marker 220. Therefore, how far did I actually travel in that time? Well, it would be 220 minus 100, which is 120. Another way of thinking about that is if you had a record of just the speed, right? So Noah's driving, I said Victor was driving. No, I said Noah was driving. Because you guys are sitting like this, and I was thinking if you're in a car, Noah would be driving. And Victor could be looking at the speedometer, and he's just keeping track of the speed the whole time. We start the clock at the same time, and you notice, okay, you're doing 60. And then he keeps putting a bunch of dots every couple seconds, and you end up with, yep, we've just been going constantly 60 for a total of 2 hours. And then we get to the diner after we get to our place, after we exit on mile marker 220. I'll leave that there. And I ask Noah goes to the bathroom, I ask Victor, how far did you go? And all he has is this right here. What's he gonna do?
2 times 60.
Right. And so he says, okay, 2 times 6, because we went 60 miles per hour, and we went for 2 hours. And even that's the great thing about this is the units also cancel out. You take hours, divide by hours, and you're left with 2 times 60 is 120 miles. Right? Now, the cool thing about this, a lot of cool things about this, is that this has a cool geometric interpretation. That 60 is the height of this rectangle, right? 60 units high, 2 units wide. And so 60 times 2 is the area of this, I said triangle, it's a rectangle, right?
Yeah.
Okay. Now, so that's just a refresher. That's one reason why we might want to calculate the area of, and one thing I didn't do is say this is the velocity of t. And what's the formula for this function?
So x equals.
How about t?
Oh, yeah.
So velocity is equal to what? Now forget that. There's a straight line.
Just 60. Yeah. V equals 60.
It's just 60 in this case, right? It's a constant 60. And you could think about that as, okay, we have an mt plus b, the slope is 0, so that goes away. It goes through here at 60, and so it's just 60, right? Now, this is one example of when you might want to find the area under a curve. In this case, the curve is not curvy, but remember we call any kind of thing that you draw, any function you draw, we call it a curve. So the area under the function, in other words, between the function itself and the input axis here, right? That area, this is one example of why you might want to find that area. Maybe we want to find this area. This is another function. It's on some domain. Maybe for whatever reason we'd want to find its area. That's doable here too, right? You could just say, well, we could break this into a triangle. We know the formula for that. Break this into a rectangle. We know the formula for that. So you have an A1, A2 here. A1 is 1/2 the base times the height is 120, right? So that's just 120. A2, it's a rectangle, so it's just 2 times 100. So it's 200. And we just add those together and whatever. I guess you get 220. Thank you, 320. 320. Who cares? But that's not part of this problem. That doesn't mean anything in this context. I'm just saying maybe for whatever reason you might want to find the area under this curve. You could do it because everything that we're dealing with is straight lines, and you either have a triangle and a rectangle, or you have a rectangle, or you might just have a triangle. Whatever. As long as things are just straight lines, who cares? Now, one thing I want to say before we move on, in your homework, you're going to need to know that the area under a curve of velocity is so if velocity is in distance over time, then the area is distance, right? So, okay, all right. Just so you know, for your homework, it's going to say, what's the distance traveled? And it's going to give you something like this. And you're going to find the area. Because that's, okay, because we've done this before, I'm not going to go into that. All right. Okay, but there are 1,000,001 reasons why you might want to find the area under a curve. This was just one example of why you might want to do that. So, but now we run into a problem when the curve itself is not a straight line. So for instance, this curve that I'm going to draw is actually curvy. And we want to know, so here's our problem for today. We want to find, going from 0 to 1, the area under this curve, f, from 0 to 1. That's going to be our project for today. Okay. One thing, just to notice, I could tell you it has to be less than a half. Why? Well, because, you know, here's your curve. If it goes like this, and the straight line is like that, and the height is what right here? 1. And the base is 1. The triangle, the area of the triangle has to be bigger, right?
Yeah.
And the area of that triangle is 1/2 the base times the height is 1/2. And so I know that the actual area that I'm looking for has to be less than that. Yeah. Okay, so we're going to use that to kind of check our final result today, but anyway. But okay, here's the thing. How are we going to find that? Well, there's a bunch of ways we could do that. And in general, these are like the steps that we're going to take. One, we're going to partition the domain. What do we mean by that? Well, the domain is the input values of the function, right? And in this case, yes, x squared, the domain of x squared is all real numbers, but we're only concerned with this right now, so I'm just going to call that the domain, okay, from 0 to 1. Partition, what do we mean? We're going to chop it up. And we're going to chop it up into equal sizes. It's not necessary to do that, but for the first few years that you're doing this kind of thing, you do it in equal sizes, because it makes your life easier. Though it's not necessary. So I'm going to cut this first in half. Then I'm going to cut it again. So that we are right here. Equal sizes. What are the sizes here? Now, okay, so first off, the x is the domain. And each one of these is an equal length. What is that length right there? 1/4. It's 1/4. Now we're going to call this delta x. For now and forever. This is my delta x, and in each case my delta x is exactly the same now that I've partitioned the domain. And it turns out, this will be useful just to have in mind, delta x. So in general, if this is some b and this is some a, so maybe we had the same function, but I cared about the area from say 3 to 5. Right, so 9 up to what, 25 right here, and this is the area that I wanted. Then what I do is I take, well, you're taking something of length, in this case 2, right? How did I get the 2? Well, you took your final point minus your initial point, right? So if that final point is b and that initial point there is a, you would say, okay, we're going to take whatever b minus a is, and we're going to divide it into, in this case, how many chunks do I have here? 4. And look at this, right? I took 1 minus 0 divided by 4, and I got that my delta x was 1/4. Don't get caught up, because like at first, when we first do these, and the book does it too, it starts off here. And so you think, your delta x is 1 divided by whatever that number is. Not necessarily, okay? Because if we were doing it here, like I said, from 3 to 5, and we divided that into 4 pieces, then it would be 5 minus 3 over 4 pieces would be 2 over 4. It would be 1/2 would be our step size, or our delta x. Okay, so I'm just going to go ahead and do this in general, kind of giving away my hand. In general, however many pieces, n pieces that you've cut this into, that's what you'd have for delta x. You have your final bit, your final position, minus your initial position, and you chop it into n pieces. Right now we've chopped it into 4 pieces, so we have 4 blocks. Okay, so now, step 2. Choose left or right endpoints. What do I mean by that? Well, this is what we're going to do. We're going to approximate this area with rectangles. And we have a choice here of how we want to do this. We could either choose on the left, whatever the value of this is here. I'm going to do this in a different color. We take the value, and so right now I'm going to choose left endpoints and say, okay, I go to the left-hand side of this first one, and then I just say whatever that value is, and I go straight over to here. Now, I'm going to choose my next block, block number 2. I'm going to choose the left endpoint, which means I'm going to go up to here, whatever the output of that function is, and draw my rectangle over to here. Now, here's my next block. I go to the left-hand side of that endpoint. I go to the left endpoint of that, and I'm going to draw my rectangle like this. Here, I'm going to say, okay, here's my last block, my 4th block. And I'm going to say, okay, I plug in the left endpoint, get out this as an output, and now this is my final rectangle right there. Now you can see, is this an underestimate or an overestimate of the actual area?
Under.
It's an underestimate because you can see we're missing this bit, we're missing this bit, we're missing that bit and that bit. But, you know, whatever. And so what we're going to do now is just calculate this area. Cool thing about this is they're all just rectangles. It's just 4 rectangles. So the area, and from now on I'm going to say capital A is the actual area that we want, okay? So from 0 to 1 under the curve x squared, A is the actual area that we're trying to find, okay? And I'm going to say that A then is approximately, it's not quite this, but it's a decent approximation, of these 4 rectangles, A1, A2, A3, and A4. Okay? So let's actually find them. We chose left-hand endpoints, and so what I'm going to do is say, okay, what's the value there? 0. How did I get it? I took my left-hand endpoint, which was 0, and I plugged it into this function, right? And that gave me the height. And what do I multiply it by to get the area?
By the length, so 0. Or 1/4.
1/4 is delta x. I'm multiplying it by whatever delta x is. Same thing here. The second area, its height is given by, well, when I plug in 1/4 into the function, that gives me the height, right? That's the height right there. Multiply by the width, which is still just delta x. The third one, now what am I plugging in to get 3?
A half.
A half. I plug in a half. That gives me the height. What's the width?
Delta x.
Still just delta x. Okay. Now finally, to get A4, I plug in what?
3/4.
So I plug in 3/4 into F. I get the height. And I multiply it by what width?
Delta x.
Still just delta x. Now let's actually do some calculations. F of 0 is
0.
times, who cares? Plus F of 1/4 is
16.
1/16. Because F of 1/4 says take 1/4 and square it, which gives me a 16th times, what's delta x? 1/4. Plus, I plug in a half into here, and what do I get out? 1/4 times what?
4.
A 4th. Now I plug in 3/4 into here.
9/16.
3/4 gives me out a 9/16. So that's the height right there. 9/16 is how high up you are. Multiply that by delta x, which happened to be the same because we chose it to be, because it will make your life easier if it's the same. Doesn't have to be, but everything we're about to develop will still work if you chose different values, but why would you do that? So, here we go. 0 plus, I'm just going to cut to the chase. I already did this. You do a bunch of stuff, you get it all over 64, and it comes out to be 7/30 seconds, which is 0.21875. So that's one estimate. That was the underestimate, right? We know that that has to be less than the actual value of A. So I'm going to start keeping track of all this. Okay. The actual A that we care about. It must be greater than the underestimate that we got, which is 0.21875. Now let's return to, I didn't write down all the other steps. The other steps are just what we did, okay? Like, you're gonna do this so much, you don't really need to write steps down, but this is the idea. So now, instead of choosing left endpoints, let's see what happens if we would have chosen right endpoints. Okay, so coming back to where we were, say, okay, our first block is here between 0 and 1/4. Now I'm going to choose the right endpoint of that block as my first rectangle. Here's the height of my first rectangle. But now, instead of going over here, this is the block I care about, so I'm going to bring the top of the box back that way. Now, for this block, which endpoint do I want to take? So I go up to 1/2 and I draw my box coming back like that. Here, I want the right endpoint, so I'm going to plug in 3/4, get up to here, and get my block coming down like that. Finally, the last block, I'm going to go to the right endpoint, plug in a 1. I get out a 1, and I go over, back, however far delta x is, and I get my fourth box, which looks terrible because I'm like writing it like this and I can't see. But is this an overestimate or an underestimate? It's an overestimate. As you can see, we're picking up all this extra area that is not there. So we're pretty sure that whatever this is going to be, here's my A1, here's my A2, here's my A3, and my A4, that's going to be an overestimate. So whatever we get here should be greater than A. The actual area that we care about. Now, okay, let's see what this looks like. What's the height here? It's f of what?
1/4.
1/4 times delta x, right? Because the height, that's the height, delta x is the same, it's still just 1/4. Okay, now how do I get the height of A2?
F of 1/2.
F is 1/2 times delta x. What's the height of A3?
F of 3/4.
Whatever you get out when you plug in, that value gives you the height. That's the height. What's the width?
Delta x.
Delta x. And now finally, how do we get the last one?
F of 1.
F of 1 times delta x. And we could do all this. This gives you a 16th times 1/4. A half is 1/4 times 1/4. Plus 3/4 gives us the 9/16 times 1/4. Plus f of 1 is what? 1 times 1/4. And you do some calculations and you find 15 30-seconds, which is 0.4875.
Like average something?
Well, you could, but there's a better way. There's a much better way, because watch it out. Okay, so now we know that. The average may or may not help you. I don't know. I mean, it would certainly get you closer. Well, or would it? It depends. It depends on how curvy this function is. Because if it's not very curvy, one of these might be pretty close to the actual answer, and one of them might be way off. That can happen. The closer this thing is to a line, like if it's a line and you do this, then the average would be the actual value. But if it's not a line, who knows which one's actually closer? I don't know. There's probably a way of figuring that out. That's not what we're gonna do. I'll show you what we're gonna do. It's a good guess, though. You could average it. And if you had to do this really quick, maybe you take an average and say it's around there. So it's between there, so if you take an average, it might be closer to the actual value than one of those. So yeah, that's one way of doing it. Here's a better way. You'll notice that we're going to do the same thing. We're going to take our function on this domain from 0 to 1. And when we partition the domain, now let's chop it up even finer. Instead of chopping it into 4 bits, like we did before, let's chop it into 8 bits. So I'm going to go here to 1/8, 2/8, 3/8, 4/8, 5/8, 6/8, 7/8. Now we could choose either the right or the left endpoints. We're not going to go through because this would take forever to actually do this. I just want to show you visually what's going to happen. I'm going to choose right endpoints. Okay, so I'm going to get this block. I'm going to get this block. And then I'm going to get this block. I'm going to get this block. And then I go here and I get this block. I go here and I get that block. I go here, that block. And I go here, I get that block. You can imagine that the finer we make this partition, the more bits, the more pieces we chop this into, the less area we end up with over on top of this guy. Yeah. You see what I'm saying? And so like eventually, so we could, if you were so inclined, calculate this, and you'll see like that both the overestimate and the underestimate would be between this. So what you'd end up with is something like this. So the new overestimate that we get here, let's just call it A2, would be less than the last one that we got. And we could see that it is still bigger than the actual area that we want, right? And we could see that if we did the underestimate here, it's still an underestimate, but it's a better underestimate than this guy. And the underestimate, let's just call it AU. Let's do that. A overestimate is bigger than A, the underestimate, but it's still closer to A than when we did it with 4. Okay, you got an underestimate here, underestimate here, underestimate there. Right. And now I think you can imagine what happens as we take n to get bigger and bigger and bigger. Right? Eventually, maybe one might say in the limit, right? In the limit, this overestimate gets so small, right? If I've chopped them up so fine that it's doing something like this, right? That overestimate is going to, as n increases, that error is going to go to 0, right? So, okay, that's the idea. And in your homework, you're going to do this with like varying sizes. It'll tell you to do it with 4. And then it'll tell you to do it with 8 and do this calculation that we just did and show like, yeah, it's getting bigger. Like, I'm not going to bog you guys down with a ton of those. That's why there's only a few of these. Because I think after doing it once or twice, you get the point, okay? And so we're not going to waste too much time, but I do want you to see it. And it's good to actually calculate it, go through the motions of what you're doing. Plugging in a value, multiplying it by a distance. Plugging in a height, plugging in a value to get a height, multiply by distance. Add that to plug in a height, multiply by a value to get a new distance. That's a good exercise to do. And so, now in general, this is what we're going to do. Actually, not in general yet. We actually want to do this for x squared. So this is what we're going to do. It's the same thing. The exact same thing we did before. F of x is still equal to x squared. we're still on 0 to 1. Now what I'm going to do is chop this up into n bits. So, and now this will be useful to say whatever my left-hand endpoint is here, I'm going to call, it happens to be 0, I'm going to call it x0. This is going to be x1. This is going to be x2, and so on, all the way up to xi, all the way up to the last one, which happens to be 1, is going to be xn. Notice there's n plus 1 bits here, right? Yeah. Just like when we chopped up 0 to 1 and we did it in 4 pieces, right? We had a total of, this would be my x0, x1, x2, x3, x4, right? That's a total of 5 guys right there. There's 5 points. Yeah. But we're only choosing one side, either the left or the right, to get our heights. And so if you choose the left-hand endpoint, you're going to choose 0, 1, 2, and 3. So over here, if you're choosing them, you're going to go 0, 1, 2, all the way up to xn minus 1. If you're choosing the right-hand endpoints, which makes your life a little easier, then you get 1, 2, 3, and 4. Or over here, you would get 1, 2, all the way up to I, all the way up to xn. And that's what I'm going to do here. I'm going to, yeah, right? How many of them? Well, 1 through n is n. How many of them? Well, 0 through n minus 1 is n, right? It's just 1 through n. Much easier. And that's how we're going to do this. It works if we choose it the other way. I'm just going to choose the right-hand endpoints to make my life easier. And so, this is what we're going to do. We're trying to find the area. So, I'm going to say, okay, let's choose right-hand endpoints, and we have A1. Here's A2. And so on, all the way up to, let's see, A1, A2. This guy is, xi is going to be AI, right there. Right, so here's A1, A2, all the way up to the ith one. And finally, the last area bit that I'm going to get is this guy right here, which I'm going to call AN. And I'm going to say then that the area that I want is approximated by, is well approximated by A1 plus A2 all the way up to AI. And finally we end at AN. How do I find A1? What do I do?
x1 times
x1?
Oh, f of x.
F of x1. I plug whatever that input value is, I plug it in to get the height. So my height is given by f of whatever x1 is times
1 over
let's just call it delta x for right now. Delta x. Because each one of those is delta x. And we're still working on this concrete value here. This one's going to be 1, that one's going to be 0. And so let's actually find delta x. Delta x is I go to the end point, minus off the other end point, and I divide it into how many pieces? N. So delta x is equal to what?
1 over n.
1 over n. Okay. We'll need that in a second. Then how do I get A2?
F of x2
F of x2
times delta x.
delta x. How do I get the ith one?
F of xi.
F of xi times
Delta x.
delta x.
F of x.
Finally, f of what?
xn.
xn times delta x. I bet you there's an easier way of writing this. Well, we're not there yet. We only have n things. But yeah, that's where we're going to go. How about, and this is a nice thing about doing the middle one, as you're doing this, it's going to, now this homework, you're not going to go into all of this. That'll be the next time. You don't have to do that. But I want you to see this. I want to go ahead and do this today. So this is what we're going to do. We're going to say, okay, it's really useful to have a general one right there because it can give you a formula really easily. But I'm going to say, in general, what you do is you plug in the ith one still delta x the whole time, as I goes from what to what?
The 0 to infinity.
As I,
Oh, 1
as
to
the index goes from where?
1 to n.
Oh,
1
to n.
Oh, to n.
This is just this, I'm just rewriting this sum right here. There you go. And that is an approximation. A is approximated by this guy. So I'm going to say the area that I want is approximately equal to that. And the bigger that n gets, the closer that approximation is. So now, okay, let's figure out a formula for the xi's. And this is pretty simple. Because you could, this is how I like to do it. I like to say, okay, whatever your start point is, just start with your x0, whatever it is, and then you're just going to add on a delta x, right? That would get you to x1. Yeah?
Yeah.
Right? Like, if I started at 5 and my delta x were, I don't know, like 1/3, I would say, okay, how do you get to x1? Well, if I started at 5, I would just add on a third, right? So in this case, x1 is just 0 plus 1 over n. Okay, what is x2? Well, you go to x1 and you add on a delta x. That's how you step over one bit, right? You just do that again. But x1 was what? 1 over n plus another 1 over n. That's the same thing as 2 over n. And in general, basically, in other words, how many steps have you gone over? Well, it's however many x to the n's there are. And in general, what you could say is then xi is just whatever x0 was plus I times whatever delta x is. Does that make sense?
Yes.
Right? So if I take 5 steps, it's like starting at x0 and going over 5 times whatever delta x was.
Yeah.
Right? Yeah. Just to be sure, let's just make sure that this works over here with our original thing that we did. Right? This formula should work. We could find our xi by taking x0 and then going I times delta x. What was delta x in this case?
1/4.
1/4. Okay, so x0 plus I times 1/4. What was x0?
0.
0. So it should be 0 plus I times 1/4. So when I plug in a 1, I should get 1/4. Does that happen?
Yes.
When I plug in a 2, I should get 1/2. Is that what we get?
Mm-hmm.
When I plug in a 3, I should get 3 over 4. Yeah. When I plug in a 4, I should get i's 4. 4 over 4 is 1. That's where we end up. So this is a very, very nifty formula to have right here. Okay. Okay, so f of xi, then, in this case, should just be, so what was x0?
0.
0 plus I times, what was delta x for our, this case?
1 over n.
1 over n. So my xi should be 0 plus, how about just write it as I over n? Okay? Okay, so I take the sum as I goes from 1 up to n of f of I over n times delta x. What was delta x?
1 over n.
1 over n. 1 over n. All right. Ready?
Yes.
Okay, now. Okay, I'm going to get rid of all this down here. Should be good. Should be good. Yeah, okay. I don't need any of that. Okay, now. What is f of something? In this case, what is our f?
X squared. X squared.
Okay, so I take whatever that is, plug it into this function, and it tells me you take that thing and square it. Yeah. So that thing happens to be I over n. Now I'm going to multiply that by 1 over n. Let's rewrite this a little bit. Now you're not doing this time. Next time you're going to do this so many times it's going to make you sick. But here we go. That's I squared over n squared times 1 over n. So that's the same thing as I squared over n cubed. Now does n change as we change I?
No.
It's always whatever it is. If I had chosen 5, we'd have 5 cubed down there. And 5 cubed would be in every single one of these things, right? We would have 1 squared over 5 cubed plus 2 squared over 5 cubed plus 3 squared over 5 cubed plus all the way up to n, which would have been 5. 5 squared over 5 cubed. I could just pull that 5 out, right?
Yeah.
Right, that over whatever, as long as it doesn't have an I in there, it's constant as far as this is concerned. I could pull it out, that 5 cubed, and I'd still have something like this. Right? So that's what I'm going to do. That's what I'm going to do with that constant. N, in this case, is just a constant. And so, I'm pulling them out, and I get 1 over n cubed times the sum as I goes from 1 up to n of I squared. Now, if you remember, last year, we actually proved what this is. It might have been in your homework, we might have done it in class, I don't remember, but I know that I had you do it because I was anticipating this.
Vaguely remember.
There's a formula for it that you had to prove. That formula turns out to be, it's in terms of n. Where is it? Where is it? N times n plus 1 times 2n plus 1 all over 6. So in other words, 1 squared plus 2 squared plus 3 squared should be the same thing as 3 times 3 plus 1 times 2 times 3 plus 1 all over 6, right? That's how that formula works. And I know that you guys proved it last year. Let's just, I'm curious. 3 times 4 times 6 plus 1 is 7 over 6 is 3 and the 2, so 2 times 7 is 14. That's 1 plus 4 plus 9. Yep, it's 14. Okay, all right. Doesn't prove it, but okay. So that formula works no matter what n is. I could have done a 4, right? When I chopped it into 4 and we got the right-hand endpoint, right?
Yeah.
Like, let's think about that. I want to put that back up here. I want to drag this point home. We plugged in a 4 for this. When we did right-hand endpoint, we got that area, so I'm going to call it area 4, was well, let's do it this way. The actual value was 15/32, which was 0.46875. That was the overestimate. That's what we're doing here. So it should be the case. That's the overestimate, right? Because I'm starting on x1 and not x0, right? So this should be the overestimate. And if I plug in a 4 for n, that should give me that. Let's check it. 1 over 4 cubed. 4 times 4 plus 1. 2 times 4 plus 1. All over 6. Jeez. Okay, so let's cancel one of these 4s. There's a 4. We'll take him down to 2. Yeah? So that's 5. 2 times 4 is 8. 9. 4 squared is 16 times 6. Did I do that right?
Yeah.
9 is 3 times 3. This is 2 times 3. So there's 3 times 3. Here's 2 times 3. Those guys are gone. We have 15 in the top.
Over 30.
2 times 16 is 32. Hey! Alright! Okay, good. I feel good about this. That's nice. So, in other words, all we've done with this nifty formula that we have is we've just said, okay, again, this is what a formula is. You could go and plug in the values ahead of time, right? Like we did when we first calculated that A4 was 15/32. We could plug in those values ahead of there, or we could do all the work in general and plug it in here at the end.
Could I just use that on the homework?
Good luck. Well, this is your homework's going to be to derive this stuff.
Oh, I thought the homework was just like.
Well, not for this one. So
Oh,
hold
yeah.
on, hold on. N squared plus n times 2n plus 1.
Yeah.
Over 6. I'm just going to keep going here. Okay.
Multiply it out.
First outer inner last gives me 2n cubed
Plus 2 others.
plus n squared plus 2n squared is a total of 3n squareds. Yeah?
Plus.
Plus n. And now I'm going to put him down here as 6n cubed. Everybody buy that?
Yep.
That's the same thing as that, yeah? So that is what you would get if you did all of this. If I had done it with a 4, like we did at the beginning, you would have come out with this. Or you could have done all this work and come out with it like this, yeah?
Yeah.
Everybody with me? Okay, so watch this. I'm going to rewrite this stuff. We said that the area, in this case, for this thing, is approximated by this thing. Which we just found works out when you actually use the f and you actually use the xi's and the delta x that we found, comes out to be 2n cubed plus 3n squared plus n, all over 6n cubed. Yeah? Okay, so we're all on the same page. That's what this is. Now we're ready to take a limit.
Why wouldn't you like factor out an n and
Yeah,
then
you
cancel
can.
it?
You'll see. Well, we could do it that way. You could factor out the n cubed. You'll see. This is what I'm about to do is the way that just the way that I do it. But it's a great question. Why wouldn't you do it the other way? Basically, check this out. In the limit, the area is equal to the limit as n goes to infinity of this thing right here. As I goes from 1 up to n, f of xi times delta x. This is going to be your best friend right here for months. Which is equal to the limit. In this case, this isn't like, this is going to change if this were somewhere else, right? My xi's would have been different if I were over on 5 to 3. Or if I were at 100 to 1,000, right? My xi's and my delta x's would have changed. So it's not just like, x squared gives you this. No, it doesn't. We'll get there. We'll get there. The limit as n goes to infinity of 2n cubed plus 3n squared plus n over 6n cubed. Now, yes, we could have factored out the n cubed and we'd get to where we're just about to go. But the way I think about this is, well, hold up, n's going to infinity. That means that guy's blowing up and that guy's blowing up. But if I divide the top and the bottom by n cubed, right? Like that. Then we get the same thing, yeah? And so I'm going to factor him into the top and the bottom, and I get the limit as n goes to infinity of. So he jumps over here and kills him, leaving me 2. What happens when he jumps over and hits him?
3 over n.
3 over n. Then what happens when he jumps over and hits him?
1 over n squared.
1 over n squared. Over
6.
over 6. Now can I plug in an infinity?
Yes, because I'll just grow.
So what happens to him as n gets arbitrarily large?
He goes away.
Goes away. What happens to him as n gets arbitrarily large?
Goes away.
And so we could say that's the same as 2 over 6, which is 1/3.
Oh, it's
And there's your actual value. It turns out to be 1/3. And it is the case that 1/3, the actual area, was between the 0.218, 75, and the 0.46875. It is. And each one of these, the bigger and bigger you make n, you could get better and better approximations. Or you can just say, you know what, why don't we just let it go to infinity? Just take the limit, right? But the thing is, like, you can't do that ahead of time. Like, you know, you have to wait until you get all of this and get your formula. Once you have your formula for this specific function in this specific region, then you take your limit and you see, oh, it does approach a limit, it does approach an actual value, and it is 1/3. It would be the same thing if we had set it up with left-hand limits.
Yeah, it would just be...
Everything would have been a bit different. Instead of going from 1 to n, we'd be going from 0 to n minus 1. The formula would be slightly different. This might look a little bit different, but the limit would be the same. Another thing, there's a couple of things we need to talk about. Oh no, I wanted to do this first. So, okay, woo. Here's a question. Okay, so I'm going to get rid of all this. Everybody got this? This is the name of the game now. We want areas. We want to know what the area under a curve is for a bunch of different reasons. There's a million different reasons why you might want to. And the way we're going to do it is use approximating rectangles. We're going to take whatever that region is, divide it into n pieces, and compute n areas. The way we do that is just like this. And then, not now, not in this homework, but in the next homework, you're going to take a limit to find what the actual area is. This homework's a little bit different.
It's just doing it.
You're going to do it for,
Specific.
like, it'll tell you do it for 4.
Yeah.
And then do it for 6, and you'll see that it gets better. Another one of the questions, though, is something like this. So this is similar to questions 20 and 21. Here we go. The limit as n goes to infinity of the sum as I goes from, is it 1 to n? Yep, it uses 1 to n. Of this,
Okay.
this, so one second, determine a region whose area is equal to this limit.
A region of which function?
That's the question.
Oh.
Find a function and a domain on which this is the thing. And so right away, what you should notice is, okay, hold up. I know that the limit as n goes to infinity of a sum, and let's say I goes from 1 to n, of this thing, f of xi times delta x, would be some function, and there's some x1 up to xn that's been chopped up into these little areas, or these little lengths, delta x. And this is just a sum of all of those little areas, right? There's a height, there's a thing. It's not obvious which is the thing, which is the height, and which is the width here.
Yeah.
What does it look like the function might be?
Well, 3 choose.
No, that's just
Wait,
3 over n. That's
Oh,
just
3 over it.
That's just 3 over n.
Oh,
Yeah, I would have no idea what to do if it were 3 choosing. I have no clue. See, the trick is, it doesn't need to be written in this order. This is the same thing as I could have put delta x times my f of xi. Now look at it. What looks like the function?
Wait. Square. Oh, f of x. Probably be the square
Yeah, it's looking like something, and look at how that guy looks. He looks like an xi, doesn't he? Because he changes as I gets bigger. He starts somewhere, and every time I gets one bigger, he's stepping over by some amount. Looks like it's 3 over n. And it also looks like my delta x should have the form of something over n in this case. Because delta x, this is a key here, and I didn't say this explicitly. Delta x had better go to 0 as n goes to infinity. Right? Because if you're taking infinitely many things here on a finite whatever, you're chopping it up infinitely. Delta x, so in other words, the limit as n goes to infinity of delta x had better go to 0. Otherwise, you're going to be adding infinitely many things that aren't 0 together. You know what I'm saying? Does that make sense? Another way of thinking about it is you're going to chop this up into n pieces and you're going to let n go to 0. Well, then what's the width of those pieces going to do? I mean, you're going to let n go to infinity. How big are those pieces going to get? They've got to shrink. And so when you're looking at something like this and you want to identify, okay, the only way that this is going to make sense is if I could identify something to be the delta x. What's the delta x here?
The 3 over n.
That's my guess, is that the delta x in this thing here is that right there. Okay, if the delta x is 3 over n, then f of xi would have to be, like you said, well, it looks like that the f is a square root. So like f of z would be square root z. And so then my xi's, and look at that, that's something that steps over by delta x every time I increases. Right?
Yeah.
Right? It's the same kind of thing. This is in the form, xi is in the form of, well, wherever you're starting plus I times whatever delta x is. And we've already identified that delta x was 3 over n, or it had better be 3 over n. So I times 3 over n. That's what we're seeing. That's what that is. And so it looks like my starting point then would have to be 4. Right?
Yeah.
4 plus 3i over n is my xi. So in other words, let's just think about this, right? If n were, let's say, 3, it looks like it starts here at 4 for x0. And then if n is 3, this is the same thing as 3i over 3, so how about 4 plus i? So then this would be x0 equals 4. Then x1 would be 4 plus 1 is 5. x2 would be 4 plus 2 is 6. And then x3 would be 7, and that would have to be my other endpoint. They would be equally spaced, right? And that's what it would be if you had chopped it into 3 equal pieces. If you chop it into n equal pieces, then your I is still running from 1 up to n. And what would your endpoint be? Well, just plug in an n for I, right?
Yeah.
Right? Because let's think about it instead of like doing it definitely. Now let's actually just do it like this. You're starting at x0, which happens to be 4. x0 is 4. x1 is what happens when you plugged in a 1 right here and you got 3 over n. x2 is what you get when you plug in a 2 and you get 4 plus 2 delta x's, 2 times 3 over n, and so on, all the way up till you get to xn. Plug in an n for I, and you get 4 plus 3 times n over n, 4 plus 3, which is 7. Okay, so it's going from 4 up to 7. And what function is it? square root.
Just
Right.
the square root.
Yeah,
Yeah.
because here's your delta x. There's your f of xi. So it must be the case that your f is square root. And so the region whose area is equal to that limit is just from 4 up to 7, and it's under the curve root x. That is that. Yeah, those are tough. Those are tough ones, okay? I'm notoriously bad at figuring those out. Okay, but, or now stop for a second. Let's just say that this were the very first problem I was working on. Guess what? This would have been the answer that we got.
Yeah.
Right? I would have said, okay, let's chop it into n pieces. Okay, n pieces. Let's use a right-hand endpoint because it'll be easier. What would my xi be? Well, we would have started at 4. Delta x would have been, let's see, delta x is the final minus the initial over n pieces. What's 7 minus 4? 3 over n. So I would have said, okay, take I times delta x, which would have been 4 plus I times 3 over n. Or, oh yeah, that's the thing. That's what we're plugging into f of x, I.
Which is just the square root.
Yeah.
Right, we would have said f of xi times delta x, and we would have said, okay, well, if f of xi is this, I just plug my xi into here, and I get f of the xi, well yeah, it would be the same thing as f of 4 plus 3i over n. F is square root, so we'd have 4 plus 3i over n, and the delta x is 3 over n, and so we have this times 3 over n, and your book loves to flip those around so that you go, oh, that's the function because it's function first. No, they just love to mess with you, right? So that's part of the trick. It's like, are they trying to mess with me? What's the thing that goes to 0 as in goes to infinite? Looks like a delta x to me. So that's how you would deal with that kind of question. Okay, so finally, we have to do this. How much time do we have? Yeah, we're not that bad. Okay, have to do this. Because I've been saying this whole time, area. What the hell? What is area? Well, here's the definition. Definition. The area of a region that lies under the graph of a continuous function. Stop for a second. I don't know why they say continuous. It doesn't need to be continuous. I'm really perplexed why they say continuous, because you could have something like this, and you could still have an area.
But if there's
Well,
a gap.
Yeah, if there's a gap, then you have
That's
like
not-
an infinite. Like, well, you.
I mean, it doesn't need to be continuous per se.
Yeah.
Like that's perfectly fine. Like you just take the area here, add them together, and that's the area.
Well, if there's a horizontal gap. Then.
Oh, and you're screwed. What it should be is bounded function. Because if it's not bounded, I think what you're saying is something like this.
Oh yeah.
What's the area under that? Well, that's not bounded, right? But if it's bounded, you can find it. So I don't know why they say continuous, and I don't know why it's supposed to be bounded. Whatever. Okay, but that's how this book wants to play. We're going to play along. So under the graph of a continuous function, f is we're defining that. We are defining the area to be. It is the limit of the approximating rectangles. That is, the area is the limit as n goes to infinity of what are the rectangles? Well, there's x1 times delta x all the way up to f xi delta x all the way up to f xn delta x. That is what area is. Okay, now check this out. There's a few things I just need to say. One of them, I don't have any more. Good, okay. It turns out that once you've partitioned your domain, okay, so we've chopped these up, and now let's say you have some xi minus 1 up to, here's your xi minus 1 and here's your xi. And so we're talking about this approximating rectangle right here. Okay. It turns out that you don't need to have it on an end point. You could take any one of these in between. You could take any point in between. Let's call it x star. And you could go to there and do the triangle that way, or do the rectangle that way. It would change this a little bit. You would have, that would be like your xi star, which is so annoying. And this is how like the definition is. Any point that's in there will work. Why? Well, as n goes to infinity, this gets arbitrarily small. Right? And you could see, like, as that happens, it doesn't matter if you chose a left endpoint, a right endpoint, or somewhere in between. When you take the limit, all of that stuff is gonna work out. Okay? Another thing, like I said, they don't need to be equally spaced. You could partition your domain here at the very beginning and say, okay, here's one, here's another, and another, there's one here, here, and let's put a bunch right there. As long as, in the limit, all of those bits go to 0, everything's fine. And that should make sense, right? Like, okay, this is a really bad estimate, but as it gets smaller, it will become eventually a really good estimate. And ditto, no matter what point you choose in there. Does that make sense? Like, we're not going to sit here and try to prove this stuff, because take analysis if you want to prove that stuff. The point is, it should just make intuitive sense. Like, just look at it, right? This is really, really small. It doesn't matter what side you're on, or if you're somewhere in the middle. The height will be close enough. And the smaller the mesh gets, the better the approximation's going to be. So, okay? Okay, one final thing. Yeah, and so like, but for now and for years, if you continue on in math, for years, your partition of the domain is going to be equal distances, because it's easier. There will be a case where you might want to partition it differently, but not for a long time. So, don't worry about it. If you're given a table in your homework, say, and let's say that table is time versus velocity, say, and let's say your time starts at 0 and it goes, oh, I don't know, 1, 2, 3 seconds or whatever, and your velocity is like, oh, 0, and how about 3, and how about 7, and how about 9? It will behoove you to just graph this. Because, okay, here's my 0, 1, 2, 3. It'd probably be a good idea to just graph it and say, okay, here's my 3, my 2 is up here at 7, and my 3 is at 9. And that's all the data you have. I think you could see how you could get both an overestimate and an underestimate of this stuff. And if it's velocity, what does the air... If velocity is, say, I don't know, meters per second, and that time is in seconds, then what would the area under this curve be?
Just meters.
Meters. So it would be like how far you've gone. Yeah. Right? Okay? So, yeah. And it's, I think, if your data happens to look like this, it's pretty easy to tell which is the overestimate and which is the underestimate here. Right? There's one way of doing it. right? And another way would have been like this, and one of those looks like it's more than what the actual, who knows what's going on here.
Or what if it goes down and comes back?
Well, we don't know, right? You got, and that's, yeah, right? You don't know if you're given this. But given something like this, you could say, well, the best guess is that it's just increasing. That, like, it's not going up like this and that, and those are just one of the things you just have to guess. And in a situation like the table they give you, that's what I would assume, because it's like a runner is doing something. You're not gonna assume that as they're running and speeding up that they just burst up to like 1,000 meters per second, you know, or something like that. It's a pretty good assumption that this is the trend overall. Yeah. So, okay, guys, that's all I got. I think I've given everything back to you now. I didn't realize that I had your other homeworks for so long. Sorry about that. Okay.